Up next, we have Troy Martin here to talk to us from Aerohive about Wi-Fi configuration, troubleshooting, and everything you needed to know about it. Thank you, Troy.
Thanks. Okay, good morning, everybody. NANOG is a conference for network operators. You guys are the people who build the internet, make it possible for me to do things like download the latest episodes of Justified from Netflix. It allows me to be more intimate with my wife by sending my heartbeat through my Apple Watch across the internet. It also allows me from my basement to launch a denial of service attack against a company in India, as we learned yesterday. So just before we get going, a little bit about myself. My name is Troy Martin. I'm a systems engineer with Aerohive Networks. So basically what that means is I spend most of my days educating customers how the Wi-Fi protocol works and what they can do to make the performance of their network improve to provide additional capacity and ultimately get fewer complaints from their users. Academically, I started off wanting to study philosophy in university. I ended up in electrical engineering. I think this gives me a little bit of a unique perspective on things in the world. For example, when people start talking about PoE switches, you guys might get excited about the port density of the switches. You might be start asking questions about how many packets per second you can process. When I look at a PoE switch, I think that's a very convenient power supply for my access points. Looking out into the audience, I know there's a lot of people in the chairs. Thank you for attending this session. But to me, when I look out into the audience, I see a bunch of bags of water. You guys are essentially moving sources of attenuation that block the RF signals from getting between the clients and the access points. Also, I've worked on small networks of one access point, and I've worked on networks that grew as big as 60,000 access points. It's a pretty big network, especially in Canada. Down in the US, people like Comcast have deployments over 1 million, and it's even dwarfed in comparison to Wi-Fi deployments over in Asia. So what are we going to cover for this hour-and-a-half session? We're going to quickly review some RF fundamentals. I'll talk about some wave theory. We'll talk about doing some dB calculations so you guys can impress your friends at the beer and gear this evening. We'll talk about some design tips and some guidelines, how you can improve your Wi-Fi network, get the most out of your performance. We'll go into a deeper conversation about arbitration, just how the Wi-Fi protocol itself seizes access to the wireless medium and gets a frame out into space. Just a quick note, I interchange the terms wireless and Wi-Fi. To me, they're the same thing. I fully appreciate that there's a lot of different wireless technologies out there, but for the purpose of this talk, I use them interchangeably. We'll also talk about some troubleshooting, what you can do to improve your network, and I'll point you towards some additional resources where you can do some more reading or learning or engage socially with the community. There's a lot of people that are just as excited as I am to talk about Wi-Fi and help improve wireless networks around the world. So someone once said they first heard of Wi-Fi on Friday, and by Monday, everybody had it. So what this means is Wi-Fi's been around for a long time. It was first ratified in 1997, so it's almost as old as IPv6. But it didn't really catch on for a long time until just recently. We've seen a plethora of devices introduced onto the market. Many devices don't even support an Ethernet port anymore. The only option is to connect your device wirelessly to the network. It's also interesting, it's a gathering of internet providers, people who are building the internet, the core infrastructure-based, data center-based mindset. But in order to get that information, to get to those resources in the cloud, first you have to get connected to the network. And the way people are doing that more and more every day is by Wi-Fi. In around the 1950s, Abraham Maslow came up with a theory to kind of understand human self-fulfillment, and when basic needs were met, you can move your way up the pyramid. Today's day and age, first you need battery to power your device, and then you need Wi-Fi to get connected to the network. Who here is using the conference Wi-Fi? Pretty much everybody, right? Who wanted to make sure that Wi-Fi would be available before attending the conference? Okay. Who would be allowed to be here if there was no network connectivity, or you have to stay home so that to be reachable by the office, right? People are making decisions on which hotel they're going to stay at based on the Wi-Fi access at these places. So Wi-Fi is very dominant in how we connect to the network. Now, I'm sure everyone is familiar with the OSI model here. This is nothing new. I just want to emphasize that Wi-Fi only exists at layer 1 and layer 2. Lets the upper protocols take care of that. If you guys haven't heard about the layer 8, layer 9, and the dreaded layer 10, so layer 8, obviously our political layer. You have to get past the decision makers to roll out your network, upgrade, make improvements. Layer 9 is your economic layer. Obviously, there has to be a business rationale behind what you're trying to do. And in the wireless world, layer 10 is the aesthetics committee, right? These are the people that tell you where you can mount your access points, if it has to be above the ceiling, if it needs to be below the ceiling, mounted on walls, out of sight. Personally, I think access points are beautiful things. They're works of art, a marvel of engineering. Other people, not so much. Okay. And so we're going to talk a little bit about wave theory. Instead of showing you guys a sine wave and talking about the wavelengths and the crests and troughs, I'm showing you a drop of water landing in a pool. You see the waves propagating out. If we assume this is a transmitter, it's sending its message into space. So as long as the waves can successfully reach another radio out there and it can demodulate that signal, we can exchange information back and forth. Now, this is pretty simple. Simple view of the world. We have one transmitter sending nice, clear and beautiful waves into space. But if we expand that out a little bit more, in this case, 3 transmitters, we see some waves interfering with each other. Now, it's not a big a deal with the waves interfering with each other as they move through space, kind of midstream between the transmitter and the receiver. What's really challenging and problematic for us is when the waves overlap with each other right at the point that they hit the receiver, right at the antenna. Okay, that's where they're causing their constructive or deconstructive interference, which makes it challenging to demodulate that signal and turn it into something meaningful, the bits that you're trying to transfer. If we look at this a little bit further, so this picture might be synonymous to a lightly loaded workspace. So an office space with cubicles. You have a bunch of wireless devices in each cubicle. Everyone's transmitting all at the same time. There's a lot of waves propagating through space. It turns out we haven't invented yet the goggles or visor that Geordie LaForge wears to visualize RF and how it's propagating through space. But this is a very simplistic representation of how something like that might look like. Okay. Other things that affect wireless, you've probably all seen the light bending through a prism. We have waves that are refracted as they move through different sources of interference. So we're propagating through different wall types as they move through the plaster, if it's a steel-studded wall or a wood-studded wall. A lot of offices now have floor-to-ceiling glass walls. And so this has significant impacts on the way waves propagate through glass-based mediums. Outside walls are coated to prevent solar energy from coming in to help keep the workspace cooler. They also provide significant attenuation for walls. And we know Han Solo learned an important lesson in reflection in Star Wars when he fired his phaser in the trash compactor, and the blast bounced back and forth off the walls, almost hitting Luke and Leia. Okay. So before we get a little bit deeper into this, I just wanted to talk about some terms. So I live in a very siloed world. I focus on Wi-Fi. So in my bubble that I live in, there's some terms that we use if you want to sound like a pro, speak the lingo of other wireless professionals. Everybody's obviously heard of Wi-Fi. There's a common myth, though, that Wi-Fi stands for wireless fidelity. In fact, it doesn't at all. It's just a cool-sounding name. And there was a gentleman yesterday who actually asked if, why IPv6 hasn't caught on and why we're struggling with that. Maybe if we came up with a cool-sounding name, it'd get a little bit more traction, and grade school kids would know what Wi-Fi is, but they don't necessarily know what their IPv6 address is to connect to the network. In other terms, SSID, obviously that's the name of the wireless network that you're connecting to. You call out every letter. Instead of saying SID, like our hero from Ice Age, it's SSID. This is probably the most important gotcha, is calling an access point an AP, or an access point. It's not a WAP. You're not beating it over the stick, playing Gopher Hunt or anything like that. So we see that show up in a lot of RFPs, RFIs. People use the term WAP. That's a clear differentiator between people who are focused on Wi-Fi versus people who are trying to build networks that don't spend as much time with the technology. MIMO is an interesting one. I don't know if you guys remember back in the days, 7-Up had an advertising with Fido Dido, and there was a big debate in schoolyards, was it Fido Dido or Fido Dido? So this confusion came up at the IEEE as well, and so it must have been a slow day for them. I believe it was around 2004. They took the time to vote. Is it pronounced MIMO or MIMO? And it turns out around 65 of the people attending the meeting thought MIMO was the appropriate way we should go forward. Around 24 said MIMO. 35 either didn't care, thought it was a ridiculous question, and one poor soul actually suggested that we allow both into the nomenclature. And antennas is also an interesting one. What's the plural way of saying antenna? It turns out both are plural ways of saying antenna. It just depends on which field of study you're talking about. So insects have antennae. RF circuits, electronics, have antennas. Okay. Another thing, the last thing we'll talk about is 802.1x. Is it a big capital X or is it a lowercase x? So when it's an uppercase, that refers to the standard or the working group with the IEEE. If it's a lower letter, it's a task group or a subcommittee of the working group. So it ends up being an amendment to the standard itself. So when we start talking about things like 802.11a, b, g, n, 11ac, those are all amendments or additions to the 802.11 standard, where .1x stands on its own, okay? Okay, so enough terminology, let's get into some Wi-Fi fundamentals. So again, Wi-Fi's been around for a long time. It first came out in 1997 with the 802.11 legacy standard. It supported rates of 1 and 2 megabits. Today, that doesn't sound like a lot, but back then, you were competing against 10 megabit switches, right? So be mobile, carry around your device, and transmit 1 to 2 megs. That's pretty cool. Okay. It was a 2.4 gigahertz only based technology. It supported frequency hopping, some direct sequence spreading. It also supported infrared. Pretty much no one deployed infrared, so it's not even listed on this slide. But people had a hunger for more speeds and feeds, so the data rates went up. So the 11B standard came out, again, a 2.4 only protocol. 11G came out, introduced orthogonal frequency division multiplexing, which builds in some resilience to multipath interference. So you're able to get higher data rates in a congested environment with metal walls, metal racking, metal shelves. But there wasn't a lot of spectrum on the 2.4 gigahertz, and we'll talk more about that. But the 11A standard came out, again, same speeds and feeds as 11G, but it supported the 5 gigahertz band. And we'll dive deeper into why 5 gigahertz, sort of the holy grail in terms of a spectrum for Wi-Fi. Time evolved, 11N rolled out. After many, many years in the IEEE committee trying to roll out that standards, basically it gave many, many options to accomplish many different goals, which is one of the reasons it took a long time to come into fruition. But with 11N, that's probably when I'd argue there was this predominant shift to Wi-Fi based access for mobile devices. Introduced a lot of cool concepts. One of the biggest ones was channel bonding and multiple input, multiple output. Okay. 11AC is kind of the latest and greatest standard for Wi-Fi that you're hearing about today. We'll dive a little bit deeper on what's different about 11AC, what are the improvements it makes, and how it impacts lives as administrators and the lives of your users. Okay. So talk about MIMO. Because it's multiple input, multiple output, it has its own set of framework for referring to the number of transmitters, the number of receivers, and the number of spatial streams. So whenever you're looking at an access point and you want to get some more insight about it, one of the questions you should ask from your vendor or the APs that you're deploying is, how many spatial streams does it support? And so spatial streams is represented by the number after the colon. This is the most important number because it ultimately leads to the amount of throughput that you have. The first number is your transmitter, the middle number being your receiver. It is possible to have a 3 by 3 by 2. So you have 3 transmitters, 3 receivers, and 2 spatial streams. The advantage of something like this is that by having an extra mouth, basically you can shape the signal a little bit better and push a stronger signal more focused towards your clients. This increases the SNR that they receive, which ultimately gives them higher data rates. The higher data rates they have, the more throughput they have. Okay? You could also have more receivers. This works in the opposite direction. So now when the client talks back to the access point, if you have more ears, basically you can hear the signal better, which gives you increased SNR and obviously more bandwidth coming back from the client. With 11AC, it introduces a concept called multi-user MIMO, or MU-MIMO. Basically, it allows an access point to talk to multiple clients at the same time in the same transmit opportunity. So you might see an additional colon, an additional number show up in this. So you could have a 3 by 3 by 2, sorry, a 3 by 3 by 3 by 2, which allow you to talk to 2 client devices at the same time. So there's some people that are pushing for this change and just how we identify capabilities of access points. Okay, so I talked about 11AC. What's new and cool with 11AC? First off, it's a 5 gigahertz only base technology. So it only supports 5 gigahertz. So in my personal opinion, one of the biggest advantages of new clients supporting 11AC, it means that they have to support 5 gigahertz, which means if you deployed a dual band network that supports both 2.4 and 5 gigahertz, as the 11AC gets rolled out, all those devices that were buying cheaper radio chipsets that only supported 2.4, now they can connect at 5 gigahertz, right? Where there's a lot more spectrum, a lot more channel spreading and channel reuse that you can leverage. Okay, multi-user MIMO, we'll talk a little bit more about that. 802.11ac also supports up to 8 spatial streams. So 11N first came out, the standard allowed for 4 spatial streams. Chipset manufacturers pretty much ended up with 3 spatial streams before they started working on 11AC. So that's where we saw a cap of about 3 spatial streams for 11N. Access points that support 11AC will be capable of transmitting at 8 spatial streams, where clients will see them max out around 4 spatial streams. And one of the reasons for that is you need to separate the elements of your antenna. Okay, and in your smartphone, so your phone device, to put in 4 antenna leads to have 4 radio chains, these devices have to get quite a lot bigger. Okay. So we see that as a challenge. And we talked about the layer 10 of the OSI model, the aesthetics committee. If they think access points are ugly now, imagine what would happen if you see an access point on your ceiling with 8 antennas coming out. It'll look like spiders running across the ceiling. They will not be happy. We also introduced the concept of 256 QAM. So basically, this is a constellation chart that lets us squish more data into the symbols that we send across the wires, and we'll walk through some charts that bring this point home. 802.11n had a really complicated modulation and coding scheme. There's a whole chart that had a bunch of different data rates. You'd figure out your data rate based on if you're using short guard intervals, long guard intervals, how many spatial streams you're using, if you're channel bonding. It was a very complicated chart. 802.11ac simplified that. Basically, they came out with a base of data rates and then multipliers that you just allocate depending on what you'd enabled, number of spatial streams, short guards, so on and so forth. With 802.11n, one of the really cool things that it added was the capability to channel bond channels together. So you could bond 2 20 megahertz channels together, effectively making a double lane highway. The bigger highway, the more traffic you can send across the road, the more data you can get from point A to point B. AC introduced 80 megahertz channel bonding, 80 plus 80, so you can take 80 from over here, 80 from over there, effectively giving you 160 wide, or 160 megahertz, of 8 adjacent channels all bonded together. Okay, which sounds really impressive, but we'll talk about the limitations of 2.4, and we'll talk about why 160 and even 80 megahertz is probably not the best idea for deploying your networks. With beamforming, with the 11N standard, there's a lot of different options for beamforming, and because there were so many options, chipset manufacturers couldn't figure out the best way to implement it on the infrastructure side. And if they weren't doing it on the infrastructure side, client chipset manufacturers weren't going to invest in beamforming capabilities on the chipsets. So basically, beamforming didn't really come to fruition with 11N. So 11AC realized that, so they reduced all the options. So now there's only one option for doing beamforming. Now we're starting to see beamforming rolled out. But basically what beamforming, to make it work effectively, the access point says, hey, I have a frame I want to send. It lets the client know via a null data packet. Then the access point asks for the client to send a feedback matrix to it, back to the access point. Once the access point figures out the matrix, it figures out the best waveform to send out to that client. And then it does a specific beamform which changes some of the amplitude, some of the phase modulation to build a stronger signal out towards that client. And so if that sounds a little complicated for the 11N side, imagine what it's like when you're trying to talk to multiple clients all at the same time and beamform for each one of them. Okay. So for the QAM modulation that we talked about, so this is a really simplistic picture. So the very low data rates, you'll see some BPSK. Basically, This is referred to as a constellation chart. So if I was to give each and every one of you a bow and an arrow, and you were to draw back the string and try to shoot an arrow at these dots, basically if you aim left or aim right, you have a pretty good chance of hitting the target that you're trying to hit, okay? So this is in a very low signal noise environment. There's a high margin of error. You can still get some pretty accurate transmissions. The downside is you're not sending a lot of information. There's not a lot of bits going across with each symbol. It's a one-to-one relationship here. Each symbol is 1 bit. If we expand this out a little bit, so with QPSK, now we have targets in each of the quadrants. So maybe some guys in the first row might feel pretty confident about being able to shoot that with a bow and arrow. If we take a look in reality, this is basically a plot of multiple symbols landing in the quadrants. You can tell you don't have to bang on with a dot, but if you're generally in the same quadrant, the way the signals are processed, they can figure out where you're trying to aim and accurately count the bits. But as we keep rolling this out, so 802.11n stopped at 64-bit QAM, right? So that's quite a few targets. In this case, we can send six bits per symbol. So there's a fair bit of density in terms of the bits we're sending across each symbol. But if you look at 11AC, it's 256 bits, right? So it's very precise. You have to be archery masters, maybe even from the front row, to hit targets that are this close together. And so what this means is you need really high signal-to-noise ratio. So we'll talk about some dB math, but essentially looking at SNRs of around 40, which results in signal strength of around 50 that your client hears to hear. So in realistic terms, if you're beyond 15 feet from your access point, you're probably not getting a signal strong enough to demodulate 256 QAM. So unless you're within that 15-foot bubble or sitting on top of the access points, I noticed there are some APs that are right on the table. So if you're right at the table with those access points, you're probably getting fantastic AC speeds. But it makes it really close. But being 30 feet out, you're not getting the most out of your 11AC environment. Okay. With multi-user MIMO, basically you have so your smartphone devices, again, many of them to preserve their battery life and so on and so forth, they'll only send one spatial stream. The more spatial streams they send, it consumes some of their battery, shortens their life, it won't last all day. Their user upset with them, so they cut it down to one spatial stream. But many access points that you deploy are capable of more spatial streams. They can do 2, 3 with 11AC, 4 spatial streams. So why not take advantage of the AP's spatial stream richness and let that access point talk to multiple clients at the same time? It sounds pretty cool. And the way they do it is they create a specific beamform for each client, but there's a few conditions that need to be there in order for this to work well. One, the clients have to be sufficiently separated. Okay, they have to be, if they're evenly distributed around a nice circle, you might be able to deploy even beamforms. But if you have two clients, two people at the same table with their laptops right beside each other, it's very difficult to create enough differentiation between the beams to effectively separate the signals to those clients. So if you have enough clients that are equally distributed through your environment, then you can start looking at creating unique beamforms for them. And so in order to do that, the access point says, hey, I got frames for 3 clients that I want to send out to. So the 3 clients at the end of the bubbles that I'm showing here. Says, here's a null data packet. I have data for all 3 of you. Each one of those clients takes a turn responding back to the access point, providing indication of the quality of the signal that it heard. Once the AP hears the signal back from each of those 3 clients, it does some complex matrix math and figures out the best beamform for those clients. So then the AP sends out at the same time, it streams out each of those 3 clients, so they hear the data all at the same time. Now the purpose of these beamformed waves, or the purpose of beamforming, is to create a strong signal at the spot where your client is and create a null spot at the spot where the clients that you don't want to hear your signal. Okay, so it's a bit of a challenge there, which is also one of the reasons you need clients that are equally separated, so you can create nulls where you want them to. Once each client hears the frame, all Wi-Fi frames that are unicast transmissions get acknowledgements, okay, which means each of the 3 clients has to send back an acknowledgement confirming that it received its frame. Okay, so the first client, after it hears its beamform transmission, it responds. Then the AP goes, okay, next client, confirm that you received your transmission, so the next client responds. And then the same thing happens with the third, right? So you have this inherent delay with your sounding process just to get things set up, to send your transmission, and then confirm with everybody that they all received what you thought they should have received. Right? And for this reason, although there's a lot of highly touted great speeds and feeds that we'll see from 11AC, there's inherent slowdown just due to the sounding process with 11AC. The benefits you'll find in a lot of high-density environments, large conference centers, stadiums, particularly where you have devices that are single spatial stream only. The reduced airtime consumption gains that you have by sending streams at the same time will offset the sounding process. But to be honest, in today's market, I think there's only 3 client devices that support 11AC for the Wave 2, which is what you need to support the multi-user MIMO. There aren't a lot of test data to see out in the field how well this really works. Okay. Talk about some dB math, just to put this in perspective. So generally, your indoor access point has a peak transmit power of around neg 20 dBm, or sorry, 20 dBm, which is about 100 milliwatts. Right. So that's how much energy is coming out of the access points. So if you're sitting right beside an access point that's on the table, you have your arm rested beside it, you might start glowing by the end of tonight, but probably not. The signal that gets received by the clients, generally the rough rule of thumb, a good signal for a client to hear is around neg 65. Okay, so we're looking at about a little over a millionth of a watt. Interesting things start to happen when you have neg 70. We'll look at a specific client case for iOS devices, how they roam. Neg 70 is a trigger for them to start looking for next hop access points to connect to. Noise floor is generally around the low 90s, so neg 90, neg 92, somewhere in there. Basically, you have your noise floor, then you have the signal strength that you hear, your transmission at. The difference is your signal-noise ratio. And to put this all into perspective, microwaves transmitted at roughly around 1,000 watts. So that's 60 dBm coming out of microwave. Okay, so there's significantly more energy being generated by your microwave to heat up your turkey dinner than there is coming out of your access point. Okay, and this is the part where you get to impress your friends at the Beer and Gear tonight. Okay, so there's a couple quick rules, quick tricks to do some quick dB math. So basically, every change of 10 dB is 10 times the power. Right, so if you add 10 dB, it's 10 times more powerful. If you take away 10 dB, 10 times less energy. Okay? Same thing with 3 dB. If you add 3 dB, you have the power. If you take away 3 dB, sorry, if you add 3 dB, you double the power. If you take away 3 dB, you have the power. So you have the rules of 10s and the rules of 3s, if you've ever heard of that. Another interesting number is if you change it by 6 dB, effectively you're doubling the distance that your signal is propagating out at and you can demodulate it at. And sometimes you have some discussions, again, with layer 10 there, your aesthetics committee, why it's important to have the AP on this side of the wall versus the other side of the wall. Typical loss through a wall is around 3 dB. If they don't think 3 dB is a lot, maybe you can get them to pay 3 dB more for your project, or ask your manager for a 3 dB raise and see what happens. Okay. When we look at the 2.4 gigahertz, within North America, so both the US and Canada, I apologize, I'm not sure if Mexico has the same rules for channels. Basically, we have 11 channels that we can use. All these channels, they're spaced 5 megahertz apart, but the channels are 20 or 22 megahertz wide. So they're overlapping with each other. And so if you're not familiar with Wi-Fi and you have, hey, I can pick from 11 different choices of channels, sounds pretty good. Sometimes you go to hotels where they're using every channel in the 2.4 band. The problem with this is that those channels overlap, and so there's only 3 channels that provide you the most spectral reuse that don't overlap with each other. And so I strongly encourage everybody when deploying their 2.4 networks to only leverage channels 1, 6, and 11. Okay? So you can deploy 3 access points. You can configure every access point to be on a different channel. When you add that 4th access point, you have to reuse one of those channels. And so that's where it becomes really, really challenging and really interesting. And it kind of blends the science and art and try to find the best spot to position that access point to minimize that co-channel interference. And we have some slides that will talk a little bit more about that. So in the 5 gigahertz world, there's a potential for 24 different channels, but because of the FCC and what Industry Canada do to regulate some of these channels, there's some channels that specifically just aren't allowed to communicate on. So there's a block in the middle, channels 120, 124, and 128. These are excluded just because weather radar transmits on the same channels. This allows airports to monitor weather systems rolling in case they need to take some emergency action to ground the planes or have them circle the airports. With 11AC, there is the inclusion of channels 144 to just add another pair to that middle band. So channel 144 was added, but isn't necessarily supported by the 802.11n devices and lower. So if you're turning on a 20 megahertz 144 wide channel, some devices might not see that. As well, up at the end, channel 165. It's a little bit of a special frequency. It sits outside the uniband. Not all client devices support channel 165. So be careful when you're turning on channel 165, because not all devices will support it. And as they move through your environment, if they happen to walk into a cell where that access point is transmitting on channel 165, effectively it looks like a dead spot to that client. So understand what your clients can do. So at the top there, we're showing all the channels that are 20 megahertz wide. When you start looking at bonding, if you have 20 different channels that you can reuse, it allows you to deploy 20 access points in your environment and never reuse the same channel twice. But if you start bonding the channels together, which can appear to give you more throughput, if you bond those channels together, now you only can leverage those channels 10 times before you have to reuse the same block of channels. So if you can isolate those access points through natural attenuation sources in your environment, or maybe paint some walls with RF paint that helps attenuate the signals, maybe that's a good idea. If we start bonding to 80 megahertz wide, now we're only down to 4 channels. So we're almost the same problem that we have with 2.4, where there's only 3 channels to reuse. Okay, so your options for isolating channels becomes significantly impacted. When we bond 8 channels together to make that 160 wide, until the FCC and hopefully Industry Canada will follow, until they open up the weather radars, there's only 1 channel that we can bond 8 adjacent channels together, okay? So when they open up that band, that doesn't make things much worse, then there's only two blocks that we can put all those channels on. Okay, so let's start talking about some Wi-Fi design and drill into that. So one of the first steps when putting together your design is start the interview process. So this is having conversations with your users, your business managers, and understanding what the driver is for the business, what they're trying to accomplish, how things are getting funded, how are you going to support things. Okay, you want to start looking at your types of environments. Are you looking at deploying a wireless network in a conference space where you're trying to cram a bunch of users all beside each other, shoulder to shoulder, into the same room, where each user might have 1 device, could have several devices? Just a quick question, I'm curious for you guys. How many of you guys have more than 1 device, Wi-Fi capable device on your person? Okay, who has more than 3? More than 4? Okay, right, interesting, okay. We're starting to see that trend. People showing up with multiple devices. I myself, I have 6 devices, 3 in myself, 3 more in my bag. So there's a lot of Wi-Fi capable devices that people bring into environments. Are you looking at an office space? Are the cubicle walls? Is it open office space at one of these new funky designs where everybody can see and hear everybody? Or there's glass walls from the floor to the ceiling that you see waves bounce back and forth between the glass panels. There's a warehouse environment where they have a lot of material on the shelving. How high do the shelves go? How much gap is there between the top shelf and the ceiling? Is the product fairly static, or does it get changed and rotated out constantly? Is your RF dynamic changing? Okay, so you want to understand what your environment's like. Also, a really important question to ask is your client devices. So in an enterprise type environment where you have a lot more control over devices allowed into your network, you can standardize on specific hardware platforms. This becomes easier, right? So if you can mandate all of your devices support 5 gigahertz, fantastic, and that's the direction you should all be going, is pushing for 5 gigahertz based devices. But that's not always the case. In hotspot type environments or service provider Wi-Fi, where basically it's the Wild West of any device type that can connect to your network, you don't have a lot of influence over those devices, right? So you need to be able to support as many different devices as you can. So that's where having an appreciation of how many devices on your network are capable of supporting that middle chunk of the 5 gigahertz band, right? So the Uni 2 and Uni E. Earlier on in 5 gigahertz days, not all devices supported those 11 channels in the middle, right? So if you were using those channels, you created dead spots for your devices. 165 is another example that we talked about. Not all client devices support channels 165. So depending how much you care about devices connecting to your network, that may be something else to check. Understand if they're 1 spatial stream, 2, 3, or 4 spatial stream devices. Ultimately, that'll guide you towards how much capacity you have in your network. So if we take a simple look at this, a single spatial stream device that's not channel bonded, connecting to one access point, probably has a data rate, max data rates of around 65. So the real throughput is roughly half of that. Actually, it's closer to 2/3, but the math is easier with half. So with 11N and 11AC, roughly about 30 megs of capacity for a single spatial stream device that's 20 megahertz wide connecting to that access point. So that's 30 megs available for one device, which isn't too bad. But if you're trying to have 30 devices all connect to that access point all at the same time, so 30 iPhones all streaming Netflix, you divide that capacity out, you're left with 1 megabit of throughput available for each device, plus all the inherent overhead. If you're doing 11AC with beamforming, there's some inherent sounding that goes on and on. There's not a lot of capacity. And the only way to increase capacity is to add additional access points on different channels. And so you add those access points, you can keep adding those access points until you hit the problem of having to reuse the same channel. Now, once you reuse the same channel, you need to create isolation between those access points. So either you have enough channels that you can deploy, so those 20 channels in 2.5 or in 5 gigahertz, or you can create enough distance so that those two APs on the same channel can't hear each other. That'd be ideal. But if the APs can hear each other and the client can hear beacons coming from each access point or other transmissions from those clients, effectively you've created a giant collision domain, right? So if you reduce the capacity now, so you might think that you've added an extra access point, giving you more capacity, but now you're sharing that between 60 users in your giant collision domain, okay? Understand what applications are being transmitted, how much bandwidth each application is consuming, its requirements in terms of QoS settings, latency, jitter tolerances, some basic network design kind of stuff there, but really understand how much bandwidth you're going to assign to each device type, and you understand how much capacity you need to provide for your network. Also, very important questions to ask about growth. We're seeing significant explosions in Wi-Fi adoption. You may have a work environment where there might be 5 laptops. Christmas season rolls around, everyone's purchased the latest and greatest smartphone, they want to bring that into the office place. So now you've gone from 5 Wi-Fi devices to 100 Wi-Fi devices. There's significant changes. Also, some of the smartphone providers are changing their technology platforms, moving to cloud-based models, where all of a sudden you're backing up all of your pictures, all of your information, all of your applications up to the cloud every time you connect to a Wi-Fi network. So if you're going to watch the latest Canadians versus the Leafs game, you're tailgating in the parking lot, you're taking a lot of pictures, shooting some videos, you walk into the stadium, connect to the stadium's Wi-Fi network for the first time, now you're syncing all the video, all the images, that you took with your phone, right? So there's a significant load placed immediately on the Wi-Fi network when those devices first connect. Same thing happens when people walk into your schools, into your offices, or when they first flip off your cellular network onto your service provider Wi-Fi network. When they connect, they're synchronizing their data with the cloud. You have mounting concerns. And again, I keep going back to the aesthetics committee. I bump into them a lot. They're very concerned about where the access points show up. Good analogy I'd like to draw on are the sprinkler systems to suppress fires. The reason sprinklers work is because they have line of sight to the fires that they're trying to put out. If you put sprinklers only in your hallways, chances are they're not going to do an effective job of putting out a fire in the hotel room of where that person's staying, if they don't exist in the hotel room. Sometimes they might not like the look of sprinklers, so they put them above the ceiling. You'd think that that affects its ability to put out fire, and it does, until it floods the ceiling and the material gets so soggy that it collapses, the water gushes out, and then you're able to put out the fire. It just causes delay. Understand the coverage versus capacity planning. It's really easy to shoot RF into places. You light up an access point, you blast out signal, and you can get a signal strength. If your only goal is designing to a neg 65 cutoff, that's something that's very easy to do. But neg 65 isn't one of your only design requirements. You're looking for signal strength, you're looking for signal noise ratio, you're looking to minimize latency, packet retransmissions. But also, very importantly, you're trying to minimize co-channel interference, right? You need to isolate access points from one another, okay? In an ideal world, if we had fantastic walls that completely attenuated the signal and we're able to drop an access point into a room that maybe held 20 people and repeat this process, it'd be great RF-wise, but it'd probably cost a lot to build, and it'd be quite a few access points, but the performance would be fantastic. Understand your device density, how close our devices going to be to each other. This is device proximity to each other and how many devices are going to connect to a single access point. You can easily put on 100 devices on an access point. Again, we talked about the capacity limits of that access point. 30 megs of capacity is a lot to share between 100 users. But maybe those users aren't doing a lot with their wireless network. Or maybe, again, they're sitting at a conference or a stadium, and that stadium has allowed the ability to do instant video replays. So you have half the stadium, 10 or 20,000 people, all trying to watch a video replay all at the same time. So understand your use case. Is everyone trying to leverage the wireless network, use it all at the same time, or is it kind of sporadic throughout the day? Because it's a different use case, different design model. And always important, understand security. Right? If you're in the enterprise, you own the assets. You have administrator rights to those machines. You can push policy enforcement, security updates via GPO policies, and push your certificates to those machines, make it quite secure. But on the public side, it becomes one of the biggest challenges, and I'd argue one of the significant hurdles that service providers have when rolling out Wi-Fi networks to their users is getting the users on their network, making it easy for them to connect. If users have to go through a two-step process, that takes too long, it frustrates them, they'd stay on the cellular network. But if you can make it easy, almost cellular-like for them, where they just pull out their phone, it connects automatically, they don't have to think about it or do anything, you'll see a lot higher adoption of user devices connecting to wireless networks. And the ways you can do that while still providing a secure connection to the users and providing unique keys to encrypt their data uniquely for each individual user or device. Okay. So this is a heat map. For this picture, I'm using a site survey tool called Ekahau. It allows you to do some predictive site surveys as well as show up on site, take some measurements, report that into the system, and evaluate the performance of your network. Basically, it's representing a hotel. So I have an access point located in the hallway. You see some signal propagated into the rooms. I use one of the best practices, depending on your vendor of who you're implementing. NANOG 65 or NANOG 67 is a good cutoff for the signal strength that you're expecting to hear. But the signals don't stop at that NANOG 67 or NANOG 65 boundary. Even though you've designed your network to hit that NANOG 65 mark, signals continue to propagate. So at NANOG 82, if the client's successfully able to hear a signal at NANOG 82, it can demodulate that frame and actually reserves the medium because it assumes the frame's going across the airwaves. You'll find Wi-Fi, it's a very polite protocol. Sometimes I refer to it as a Canadian protocol. It says sorry a lot. It's very respectful and takes a turn when it tries to get access to the medium. And because of that, there's a lot of inherent delay in the protocol. So here's a little bit better demonstration of the channel reuse. So if we look on I guess it would be your left-hand side. So with our colored hexagon cells, we're using the 2.4 band. We have 3 channels that we can reuse, right? So you don't have a lot of different options for that 4th access point on where you can place it so those channels aren't overlapping. There's probably a good chance the red cells, channels 1, hear each other and have created a giant collision domain for client devices on those cells. In the middle, I'm showing 8-channel plan. So this is if I'm using the lower and the upper part of 5 gigahertz. I have 8 different channels that I can mix and match in my environment. So I can create a little bit better separation for when I have to reuse channel 36. Okay, and hopefully I have enough separation that devices in those 2 cells don't hear each other. But it gets even better if I can use all 20 channels, right? I have a lot more options of where I can place access points. If I need to please the aesthetics committee, I have some different options of where I can put those access points to hide them, such that I'm not interfering with another access point transmitting on the same channel. One important thing to remember is make sure devices port the DFS band. Generally today, you should be safe pretty much in North America deploying the DFS band channels, so that block in the middle. You should be okay. It was in the past, we had some problems with devices. Depending on your environment, it's just good to confirm what your devices are capable of supporting. So the previous slide showed some nice, pretty hexagons. In reality, the way signal propagates, it looks a little bit closer to this. So this is 7 access points deployed into an office space. Just because we're using 7 access points, there isn't a really effective way to lay out these APs so we don't have 2 APs transmitting on the same channel. So on the left-hand side, you see the 2 green sections. They're overlapping with each other. Effectively, we've created a giant collision domain for these users. So we've significantly cut down on the capacity of our network. So here's a picture, again, showing the different access points transmitting. At first glance, it looks nice. We see 7 pretty colors, the same colors that were used twice. The problem here is we've done a 2.4 gigahertz base design. You'll see this often a lot. I do a lot of traveling, and I see this in hotels quite a bit. They decide to use all channels in the 2.4 band. So you get channels stepping on top of each other. So this picture, color-wise, it looks good. We have adjacent channel interference in this scenario, which reduces the available capacity that we have for our network. It creates frustration, so you might see guests of that hotel provide negative feedback or choose not to stay in that hotel again. Co-channel interference. So in this scenario, all the access points are configured to be in all the same channel. So we have a giant collision domain. There's some interesting things you can do infrastructure-wise. If you have clients on the left-hand side of the network who can't see what's going on the right-hand side of the network, the infrastructure could be smart enough to send transmissions at both locations, but generally it's a giant collision domain, and the only way to add capacity is to create another overlay of access points, again, all in the same channel. So you double the access points to provide additional capacity. So sometimes I hear, like, isn't Wi-Fi just like Ethernet? Isn't it just the wireless version of Ethernet? And there's some fundamental differences between Ethernet and Wi-Fi. So first, if we look at Ethernet, it's a CSMA-based technology, but it uses collision detection. So I'm sure you guys are all intimately familiar with Ethernet, but just to talk a little bit about what it does is because it can transmit and receive at the same time, if an Ethernet switch starts transmitting a frame and it hears a frame coming in from another device, it immediately stops, sends a jamming signal, and according to best practices with switch design and number of switches you have, there's a specific amount of time that you need to jam the signal so that every device on your network can hear it. So immediately, after receiving a jammed signal, you can tell everyone else there was a jam. The 2 devices that realize they had a collision, they'll pick a random back-off timer and increase their hold-off time, and everyone can get on moving. But you're not checking every time to make sure that you can detect collisions in essentially real time on the wired side. Now, if we look at Wi-Fi, Wi-Fi is, again, carrier sense, multiple access, but it has collision avoidance, right? So it's not able to detect when a frame comes in. It's unable to listen and receive at the same time. So every time it tries to transmit, it has to try to avoid the problem of interfering with another signal, which causes some inherent delay and some inefficiencies with the protocol. Okay. In order to accomplish that avoidance, it looks at a few different things. So it has a physical carrier sense and a virtual carrier sense. Now the physical carrier, basically it's looking at a clear channel assessment. It's doing a raw energy detect to measure if there's ambient energy in the environment. And if it's a certain threshold, basically the access point or the client, so that the radio says, whoa, there's too much energy out there, I'm not going to transmit. So this could be Wi-Fi energy, or it could be energy from another source of interference, from a microwave, a generator, a Bluetooth device, if you're right beside that. Some other form of energy, if it's at a certain threshold, it's not going to transmit. And it keeps checking to see if that energy disappears. Another thing that it does is every time a frame passes by the radio, inside the field of that, inside the header, the 802.11 header, there's a network allocation vector field, which is basically a timer. And that timer says how long it's going to take to send the data that I have to send, wait a gap, and hear the acknowledgement. So that sequence is what's found in network allocation vector. So if an access point is waiting to get access to the medium, it listens for frames going by. Here's a network allocation vector. Okay, oh, I can't talk for X amount of time. So it counts down that timer until that nav field gets to 0. Then it does a quick energy detect. Okay, so every frame has that. There's also a concept of the contention window. And in the OFDM technologies, so the A, the N, and the AC, they start off with a contention minimum size of 15. And if there is a collision, they'll increase that timer all the way up to giant contention windows of 1023, where they'll pick a random number in that window and count down to 0. When that number counts down to 0, if their clear channel assessment is free and their network allocation vector is counted down to 0, they'll be able to transmit. Okay, so here's a flow chart which basically describes that concept. So a frame or an access point, very excited. It has transmit a frame. It gets to do what's intended to do. It picks a random back-off timer, and then it's checking to make sure the carrier or the medium is free, the Wi-Fi medium, and it checks to make sure it hasn't heard a frame. If it has heard a frame go around, it counts down its nav value down to 0. When the nav counter hits 0, again, it checks to make sure that the energy detect is below a certain threshold. If both those conditions are true, it waits the mandatory space, which is our interframe spacing, and then it looks at that random value, random timer that it picked, and it starts counting that down. When that hits 0, and we still haven't detected strong enough energy, and we haven't seen another frame go by, that's when the access point gets to transmit its frame. Okay, so it sends it out to the airwaves, and it hopes and prays that it gets that acknowledgement back. Otherwise, it has to go through the whole process again. Okay? So it can be a very time-consuming process. And just as a little aside, with that random backup timer, I don't know if you guys have heard of the birthday paradox. It's different than the twin paradox related to relativity and everything. But in the birthday paradox, basically, what happens here is if you take a room of roughly around 23 people, there's about a 50% chance that 2 of those people will have the same birthday. Okay, so there's a fairly high probability that there will be a collision within that window. And so that's a year. We have 365 days in a year. We talked about the contention windows. We only have 15 options or 16 options for numbers that we can pick for a random back-off at about 5 clients. If 5 clients have the same thing to talk, they pick the same contention window, there's about a 50% chance that those devices could collide at the same time. When they collide, then they're picking larger contention windows. So basically you have a situation where you could have a situation where there's lots of opportunities to talk, but because there were collisions, everyone's adjusted their contention windows to be so large that they're all politely waiting, counting down their random back-off timers just to transmit. So there's a lot of inherent efficiencies there. So here's another scenario we can walk through. Basically, we have pairs of devices that are trying to talk to each other. So stations 1 and 2 are talking to each other, 3 and 4, 5 and 6 talking to each other. It starts off, station 6 at the bottom is sending data. It waits a gap between the acknowledgement frame. It gets its acknowledgement frame. So it's finished its communication. Now stations 2 and 4, they both have something to say. So they wait their mandatory space, and then they pick the random number. So station 4 picked a random number of 9. Station 2 picked a random number of 7. So no other devices are talking. There's not other interference, so it's not setting our energy detect threshold. We count down our timers, our random back-off timers. Number 2, hit 0 first. So what it does is it wants to clear the airwaves. So it sends a request to send. Basically, it's asking for permission. It's also telling our devices that can hear it, say, I have something to say, no one else talk. And within that, to request to send, the network allocation vector is set, and it has a timer for this whole duration, all the way to the end of acknowledgement. So the polite thing to do after you hear a request to send is you send a clear to send, saying all things are go, send the data that you have to send. You notice at the bottom, station 5 is close enough that it can hear the request to send. So is there a question?
Hi, I have a request to send. Louis Lee.
Clear to send.
Thank you. These multiple station topologies, you're talking about all the APs have home runs, right? You're not talking about anything with WDS, anything like that, where the access points are connecting over Wi-Fi also, right?
So like a wireless backhaul, almost like a mesh or a bridge?
Okay. So all these access points have home runs back to a switch or a router?
Yeah, so when the pictures I was showing with the maps on the diagram, all those would be, I'm assuming they're all wired in.
Okay, just make sure.
Yeah.
Thank you.
So just the follow-up to that question, if you were using a wireless backhaul, to backhaul, obviously the APs have to be on the same channel, so you're extending your collision domain. Yeah. So station 6 doesn't hear the request to send, but when the clear to send goes out, Station 6 is close enough to hear the clear to send. So that's one of the reasons that you'll send a request to send, clear to send. So if I send a request to send to someone in the middle of the room trying to talk, someone in the back of the room might not hear me. But the person in the middle of the room, when they respond with the clear to send, they're clearing the air around them. So basically, request to send, clear to send, it's a mechanism to clear the air. But it adds to the additional overhead that we have. So once the air is cleared, Station 2 sends its data, waits its short interframe sequence, its space, acknowledgement goes across. Then Station 4 still has some data to send. It counts down from where it left off, so it has 2 more values to count down from its random backoff timer. Once that counts down, it sends its data and its acknowledgement. And then when it's sending its data, the other stations hear it. They understand the network allocation vector, so they defer the medium until that communication sequence is done. So that's essentially a snapshot of how arbitration and frames are sent through the airwaves. It gets a little more complicated once QoS is involved. Basically, you have a sliding scale for your contention windows, and instead of your distributed interframe space, you have different timers based on the QoS settings that you have. So it's shorter timers to give a little bit faster access to the medium. Okay. So let's talk about antenna patterns. So depending on the antenna that you're using, basically allows you to shape and guide the pattern of the RF into your environment. You want to direct as much RF energy to your clients as you can. You're not necessarily interested in having APs talk to each other unless you're doing like a wireless backhaul situation, but you want to focus the energy down towards your clients. So picking your antenna type can help do this. And one common mistake we find is when people take a rubber duck antenna. So that's one of those single antennas, has a 90-degree bendable arm, and say, I'll just get a higher gain antenna, and it'll increase the size of my donut-shaped pattern. What it does at higher gain, you're not creating energy. If you imagine the energy coming out to be fixed, like the volume of a balloon, you can just change the shape of that pattern. So if I get a higher gain rubber duck antenna, basically what happens is I flatten my donut, so it looks more like a pancake. So I lose vertically, but I might be pushing that energy out further horizontally, okay? So I find that very useful, kind of analogy to understand how your patterns are for your antennas. The higher gain antennas, it's just more directionally focused, okay? You can't get something without trading something else, okay? So generally, your omnidirectional antennas that you find indoor Wi-Fi, they tend to have more of a cardioid type shape that you're seeing in the upper right. Your rubber duck antennas, so those are the antennas that the aesthetics committee, again, particularly avoids, the one that look like spiders on the ceilings. Those are your rubber duck antennas. Then you can have patch antennas where you could place on a wall where you'd focus 180 degrees, your energy inside the building, and prefer not to send most of the energy outside the walls. And then for longer distance shots, or if you're trying to light up a long space in a warehouse, maybe between the shelves, you might use something like a patch or a Yagi antenna for something like that. Okay. We'll take a look at some troubleshooting. So one of the key takeaways here is that clients are ultimately the ones responsible for the decision to roam and what access point they're going to connect to. With the latest standards, 11K standard and 11V standard, if both APs and clients support that, you can influence that decision, but the clients are always in charge, okay? So again, we look at this heat map going into the hotels. You can see there's a long tail that goes all the way down the hallway. Essentially, the hallway is a giant waveguide for RF energy. There isn't a lot blocking that signal, so it propagates really, really far. Whereas generally in hotels, you end up with firewalls between the hotels, and it's relatively thin walls between rooms. And you probably know this from hearing your neighbors next door that the walls between the rooms are relatively thin. So the signal has a little bit challenging time getting into the rooms. It doesn't necessarily propagate. You generally have your bathrooms right against the hallway. It has to go through a few ceramic tiles to get through there, maybe some water piping, some copper piping. By the time it gets out to the room, so if you're sitting in a comfortable chair, staring out your window, checking your emails late at night, what you missed during the day, it's one of the weaker spots to get your signal. Although right in the hallway, signal's very, very strong. Now, if you're to continue to place access points down that hallway, because you want to push that energy into the rooms, as soon as you start reusing the same channel on those access points, you create a giant collision domain, right? And you're also you're struggling with the fact that you want to push a strong signal into the rooms. And so in order to get the energy into the rooms where your clients are, you tend to increase the transmit power on your access points. If you increase the transmit power on your APs, they start sending really strong signals down the hallways. And the other access points in the hallways that can hear the same channel, they hear it on the same channel at the same time, and they contend for access to the medium. So reduce the capacity for users in your hotel. And also, if you've turned on something like channel management that automatically adjusts the channel and the transit power, because they see neighboring access points really strong, they'll automatically start trying to turn down their power, right? Because they don't want to see their neighboring access point too strong. When they turn down their power, now you're weakening the amount of energy that's going into the rooms. So now the clients aren't connecting with a strong signal and their data rates go down, right? So ultimately, the point of the story here is that you want to put access points where your clients are. The best thing to do is put them in line of sight to that access point and try balance the number of sources of attenuation between the access points so that they don't see each other directly. So if you can put your APs in your environment such that every AP has 3 walls between it and the next AP, it's simplistic, but it's relatively balanced. And the access points have line of sight visibility to your clients. You'll get good data rates, good speeds and feeds to your clients, and you minimize your contention, okay? So let's look at a specific device example, and at the bottom I have the link to Apple's webpage that explains this, and I'll use this because Apple's been done a pretty good job, I think, of explaining as much as they can their algorithm for devices roaming. So what Apple devices do, iOS devices do, they'll start to roam once they cross the NANOG 70 threshold. All right, so keep this in mind when you're designing your network. Maybe NANOG 67 isn't the right number. And maybe it's NANOG 70 or maybe NANOG 65. But you'll start to see an increase in probe requests once iOS devices cross that NANOG 70 boundary. And so if that iOS device is in an active session, if you're sending AirPlay to an Apple TV, you're trying to transmit that, the next top neighbor has to be better by 8 dB. Otherwise, it won't roam. Okay? If it's not an active session, it has to be even better by 12 dB. Okay? So what does that look like? If we have an iOS device in the middle, it has an active session to an Apple TV device. It's currently connected to an AP. It crosses that NANOG 70. It's currently at NANOG 73, and it's looking for APs that it can join. The 2 APs on the bottom have really good signals, like NANOG 67, great strong signal, NANOG 63, even better. In an active session, that iOS device would only roam to AP2, even though it's quite a bit better. And if it wasn't an active session, that iOS device wouldn't roam at all, right? It would stay connected to the current AP until there's a difference of at least 12 dB before it roams, okay? So this is why an Apple device, or any device in particular, can walk quite a ways from its access point, cross 3 or 4 access points in a hallway, and remain connected to that AP that it first encountered when it first walked in, okay? So now it's still connected, it's transmitting at low data rates, but it's holding on to that connection because they prefer to stay to an AP it knows and trusts than take the risk of trying to connect to another access point. Okay, we call that the sticky client problem. Here's a snapshot I took from a few different devices. Basically, they're all laid out in roughly the same spot, and this is by far not a scientific study or anything. I'm using a tool on the devices. So 4 of them are Android devices, 1 of them is an iOS device. I can measure the signal strength that they detect at that given moment. Okay, and you can kind of see there's a fair bit of spread between these devices, right? We have all the way from NANOG 65 to NANOG 73, which is pretty different. So I had the access point, it's set up to be on 2.4. It turns out one of my devices is 2.4 only, so I did this test using 2.4 technology. But the point of this slide is to show you the difference of what client devices hear. And so the algorithm that they're using to make their roaming decisions are unique to what they hear. And if they're not all hearing the same thing, they're taking actions at different spots in your network. So it becomes very difficult to predict when specific clients will make roaming decisions in your network. The sticky client problem that I described, again, talking about when we first walk into the building, it's a nice strong signal, users will connect to that access point, and as they continue to walk through their environment, they could be standing underneath an access point that has a much stronger signal, but they'll continue to talk back to that other access point at their lower data rates. When you communicate with lower data rates, it takes you longer to send what you need to send across the airwaves, which means you're consuming more airtime. The more airtime you consume as a client means there's less airtime for the other clients. okay, which negatively impacts their experience. So the faster you can encourage that client to move on to an access point that would better serve it, makes it better for the herd. Okay, it's better for everybody else. Okay, let's do a little bit of troubleshooting now for some clients that are connecting. And so again, I'm with the company Aerohive Networks. This is a snapshot from one of our tools. You could pull the same information out of a Wireshark capture or enable any debug tools. But basically, we're looking at the connection sequence for a client. So in order for a client to connect to an access point, it goes through first a few steps. So either it's passively or actively discovering the access point by listening. So it's just listening for beacons coming from the access point. When it starts doing an active roam, the client sends out probe requests. So it's actively looking for a network. And so anytime you guys connect to a wireless network, if you didn't already know this, your client device remembers that network. So everywhere you go, it's always looking to connect, and it's always probing for the wireless networks that your device knows. Okay, so if you were to do a capture, you'd see your device, looking for your home network, maybe your work network, the last hotel you connected to. It wants to join a wireless network, so it's trying to find that. So after whether we're using probes or beacons, we found an access point we want to connect to. The client will send an authentication request. AP responds with an authentication response. Then the association request, association response comes back. And in this case, we're using WPA2 with a pre-shared key. So we start doing our four-way handshake. We negotiate our keys. We end up with a pairwise master key. We use this to help construct the encryption for the frames going across the airwaves. We start sending out the DHCP discover request. We're trying to get an IP address to get onto the network. But the final message there, it says, client's been de-authenticated because of a notification by driver. This is an internal message that we generate. But basically, the client's asking for an IP address. It's not getting one. So what's the problem? Okay, if you were a typical user, you'd say my Wi-Fi is broken. Okay? But what this is pointing us to is that we can't talk to the DHCP server. So maybe we dumped the client onto the wrong VLAN. Maybe our DHCP is broken. Maybe we've consumed all the IP addresses from our DHCP scope. Okay, anyway, the problem here for this client is that they're not getting an IP address. Okay? If we take a look at another problem, so again, we do go through the authentication, we go through the association, we start our four-way handshake, but this time we keep repeating steps 1 and 2 of our four-way handshake. So you'll see this in a Wireshark or an OmniPeak packet capture, steps 1, 2, 1, 2, 1, 2, and it gets punted off the network. Typically, when you're failing step 2 of your four-way handshake, it ends up being a password-related problem. Okay, so this is users, they'll type in an L instead of a 1, an O instead of a 0. They might have cut and pasted an extra space at the end. You see this show up a lot. So here's a quick way to look at some of the packet captures or any debugging tools that you have to quickly resolve some of the client issues that you might see. So here's a sequence of what it would look like if a client connected successfully. They go through their exchange, they successfully finish talking about the password, they send out the DHCP request, the response comes back, they get an IP address, and they're ready to post to Instagram. Okay, I told you guys I'd talk about some additional resources that are out there. So there's it's a training and certification program published and run by CWMP. They have a series of books. They specialize in vendor-neutral wireless training. So basically, their end goal when they were first created, they want to provide education on how the Wi-Fi protocol itself works. They didn't want to focus on vendor-specific knobs or tweaks to make that platform work. But if you understand the protocol, you understand what should be done, what should be exchanged between the access point and the clients. So devices that get onto the network. Once you know what's failing, then you can look in that vendor-specific product to figure out what you need to do to resolve that issue or to increase the performance. So they basically have a pyramid of structures. They start with their CWNA book, which is essentially Wi-Fi 101. Pretty much everything I talked about today is covered in that book in much more detail. So you can pick up that book. They publish it, and you can purchase it from Amazon or right from CWMP. If you want to get a little bit deeper into Wi-Fi, they have follow-on books. So they have a book dedicated to security, right? So they talk about WEP, WPA, WPA2, all the EAP frameworks. the whole sequence of events to get devices onboarded. They talk about the weaknesses in each of those protocols in very, very great detail. So you can look at that. The book at the bottom, the CWDP, basically it's a book that describes wireless design, all the way from doing site surveys to planning out your access points, creating models for capacity planning, coverage and planning. We'll talk about that. And then the AP book is basically, it's the analysis book. Basically, your study guide is an access point and your copy of Wireshark or OmniPeak, and you're just looking at wireless frames going across the medium, understanding what happens in each of those fields. So it's very, very detail-orientated. Excellent, excellent resource. At the bottom, there's a gentleman by the name of Matthew Gast. He was on the chair of the IEEE, the 802.11 committee. He's written a series of books for O'Reilly, so he has 802.11 second edition, and then as amendment to that, he wrote a book specific to 11N and followed that on with a third book for 802.11ac. All these books are strongly recommended. Matthew does a great job basically translating the IEEE engineering speak into something a little more human understandable. But I find myself and talking to other people, you almost have to read Matthew's stuff 2 or 3 times to kind of decipher what he's talking about. Okay, in addition to the books, there's also social media. There's a lot of people that are passionate about Wi-Fi that exists on Twitter. If you do quick searches for the hashtag, or as my wife likes to say, pound, search for that on Twitter, you'll find a lot of resources out there. We can bounce questions against them, ask them about their experiences, and they're more than willing to share. It's a very open and supportive community. Also, vendors have their own groups, their own forum communities that you can go ask questions, find out more about different products. User groups also exist. There's a lot of great Wi-Fi blogs out there, so you can check those out. Also, following the Twitter stream to give you some references to which blog sites you want to go to. And there's also Wi-Fi conferences that you can attend. So the CWNP, just a couple weeks ago in San Francisco, they had a conference. They have one in North America and one in Europe, so 2 every year. The Wireless Field Day, which is part of the Tech Field Day, which I hope many of you guys have already heard of Tech Field Day. I'll say the wireless specific one, basically it's a group of bloggers that go from one vendor to the other, get updates on the latest and greatest products, and ask them some challenging questions about what their direction is for the roadmap and evaluate new products that they're bringing onto the marketplace. WBA, DEF CON has a really cool wireless village, which gives you some hands-on experience, lets you hack with some cool Wi-Fi protocols and tools. And as thank you for attending this Wi-Fi conference, I'm providing a link here where you can download a chapter of that CWNA book. It's the Troubleshooting chapter. So if you hit this link, you'll be able to download this book in PDF format. And on that note, let's open the floor up to any questions that anyone has. Oh, sorry. Yeah.
Hi, Guy Tall with VMware. I was wondering, what did you use to make those heat maps?
Yeah, so the heat maps with the hotels and the hotel. Yeah, so I used a product called Ekahau, a site server planning tool. It's Ekahau, it's E-K-A-H-A-U. It's a company based in Finland. But my personal opinion, Ekahau and Air Magnet are probably the 2 leading vendors for site survey packages. Yes, if you want it, you can visit their websites. They're great products. Use them pretty much every day.
Phil Rosenthal from IS Prime. So if my understanding is correct, there's, because of the whole overlapping with the wide channels, you end up with a maximum of 1 channel only at 160 megahertz, and you could have 2 more non-overlapping at 80 megahertz, which basically gives you 3 channels. Is that the best practice, looking at it like the old way of 2.4 gig where you just have 3 channels and deploy it out that way? Or is there another best way of doing it if you want high data rates in your full coverage?
Yeah, so it's an interesting design question. So basically, just to summarize your question, is what's the best channel width plan to use to get the maximum capacity?
Yeah.
So the 80 megahertz and 160 megahertz, those are features that are coming out in wave 2 of 11AC. So not many devices support those right now. Down the road, you get your best capacity by not duplicating the same channel. So we're going to provide the most capacity you can. If you can isolate an area, such as rooms such as the neighboring room doesn't hear that access point using the same channels, that'll give you the most capacity. So if you can do a design like that, where if you deployed a 160 wide and the next room another 160 wide and those two rooms didn't hear each other, that would give you the best capacity. The reality is there's not a lot of locations that are designed like that, and Wi-Fi propagates really, really, really far. There was a test done by Chuck, and I apologize, I can't even say his last name, but basically he was standing at the Levi Stadium, and with two iPhone devices, he connected to another iPhone acting as a hotspot 100 feet, or it was 185 meters away, and he was getting about 15 megs down, 185 meters away. So the signals propagate really, really far. So to answer your question, I encourage all of my customers and partners to build designs based on 20 megahertz or 40 megahertz. I believe that 160 megahertz is really only useful for homes or residences, but as soon as you move into multi-dwelling units, the signal propagates too far and you start interfering with your neighbors. And 80 megahertz, again, there's just not enough channel reuse that you can leverage because the signal propagates too far, that you end up creating too much co-channel interference that ultimately reduces your capacity. So to answer your question, 20 and 40 megahertz is where I recommend everybody to go.
So doesn't that end up leading to the terrible days of 802.11b where, you know, if you live in an apartment building, you're just going to get clobbered by all of your neighbors if everyone's just going to say, ooh, 160 click, and, you know, now everyone's running on the same channel?
Yes, that'll happen. And so part of it comes down to marketing with residential and SOHO grade routers. They want to advertise the latest and greatest speeds. So like, hey, we do multi-user MIMO, we do 160 wide channels, turn this on at your house, make it happen. And the problem is exactly what you described. Everybody will be stepping on everybody else. And because it's one person in a house administrating their own network, it becomes very difficult to manage and configure. If you had a management platform where you could synchronize the channels that every access point was communicating on, holistically across like a municipality or an MDU or something like that, you'd be more successful. But or have a polite conversation with your neighbor and say, hey, maybe you want to turn it down.
All right, thanks.
Those channels. Yeah.
Hi there, Lee Waterworth from BlackBerry. Wondering about the average non-consumer access point integration between IPQoS and how long it's going to wait to transmit. So if I'm doing voice over IP across this, is it going to delay those packets for far too long and start garbling the conversations, or is there an integration between those layers?
Right, so related to Wi-Fi and QoS, it ends up being more complicated, so I didn't discuss it in much detail in this presentation. But basically with those the diff spaces and the contention windows, if you enable higher QoS values for devices that are using voice or video, it shortens those contention windows and the gap that it waits between the frames. So it'll wait shorter periods of time. It increases the probability of it getting access to the medium, but it won't starve out other classes of the traffic. So there is risk that you could negatively impact your QoS applications because other frames need to be transmitted.
Is that basically a default behavior on most access points that it'll work that way, or do you have to explicitly call that out and configure that?
You need to enable it. So some access points will have that turned on by default. Some applications will automatically tag themselves, or you need to override their tags to mark them into the appropriate queues. But once they get marked and set properly, then the random backoff timer and the interframe gap will come into play to increase the probability of those applications getting access to send their frames before other applications.
Great, thank you very much.
Yeah, no problem.
Yeah, thank you very much for the talk. My name is Sri Fawad from Alcatel-Lucent.
Yeah.
My question is, I know a lot of access points have features where they try to auto-select the best channels. What do you think of those features, and would you ever recommend using them?
So the question related to the ability to auto-select to transmit power and what channel should I be on. I would, so in my past, I used to work as a wireless consultant, so I've worked on many different vendors' products. And some vendors do a better job of explaining exactly how their auto RF protocol works. I find generally that no matter what platform you're implementing, you need to deploy it such that it meets your design requirements. And by default, out of the box, I'd argue that no one has the optimal default settings for their radio resource management or auto resource management. So you need to tune those auto channel planning protocols specific to your design environment. If you don't have a lot of insight into how it works, it makes it difficult to tune. But you have a trade-off between doing that versus statically assigning channels to 100 different access points, or having statically assigning the transit power to all those different access points and the inability to react to changes in your environment. I'd argue if you have a good design, that you have primary and secondary coverage from enough access points that if one AP was to fail, you don't need to take a lot of dynamic changes in your network to compensate for that failure, but it comes down to a design question. So it's kind of cheating on your question. It depends on how much information you have on your planning tool, whether you'd like to use it or not. But implement what you design to. I'd recommend against putting together a poor design and then hoping that my auto tuning program or protocol will take care of that.
Thank you. I guess I'm speaking from a more residential perspective where there's high density. A lot of times new neighbors come, they buy new access points, they change channels. So if you're constantly, even if you have a design, and then a new neighbor comes and they come on the channel that you're using, right? I mean, do the auto feature, do they have the ability to react to those types of things? Or do you have to constantly keep monitoring and then updating your configurations?
So there, it depends on which product you're using. So sometimes they'll describe, hey, I have this really cool feature. I do auto channel selection, but I only do it the first time my AP boots up, and I never do it again. Where other access points will do it once a day. So at 2 in the morning, they might evaluate what things look like. Hey, oh, there's not a lot of utilization on this channel. I'm going to pick it. But things are much different at 2 in the morning than they are at 4 o'clock when someone plugs in their new shiny access point that they have. So in the environment that you're describing, it's a very dynamic environment. I would recommend continually checking what channel you're on, what channel your neighbors are on, and trying to find the least loaded channel that's being used. It's a little more difficult in channel in the 2.4 gigahertz space. Often I see people that are using 5 gigahertz only at home, which gives them a lot more options for what channels they can use. And generally in residential space, you're not seeing a lot of neighbors, so maybe you can get away with 40 meg wide or even possibly 80 meg wide channel. But I'd constantly evaluate it. Tools to look at that are things like Insider or Wi-Fi Explorer on OS X. Really good tools to quickly take a look at that.
Thank you very much.
Yeah, you're welcome.
Kevin from Burlington Telecom. We have a lot of residential customers, and with the residential routers that we have, all the clients are always on the 2.4 gigahertz. Even if the 5 gigahertz is available, unless we name them differently, they always see the stronger signal on the 2.4. The corporate deployments we have, obviously we can do some band steering to a certain extent, but I'm just wondering, is that the current state of the industry? Are we trying to work with the CPE vendors to see if they can futz with the drivers? Are there upgrades coming to some of the residential style routers to include band steering?
Great question. There's a bunch of different factors that come into play with this. If you look at 2.4 and 5 gigahertz, if you set both radios to transmit at max power on both those bands, 2.4 tends to propagate a little bit further in space. And technically, that's not entirely true, but a simplistic version of this is 2.4 goes further, which means that if I walk into my house, I'll hear that 2.4 signal first before I hear the 5 gigahertz. My client device will connect to the AP on 2.4. And as I walk into the house, my signal gets stronger. So I'm a happy client. I'll stay in the 2.4 band. And unless I disconnect from the network in the house and reconnect, my client generally won't take advantage of moving to the 5 gigahertz. And so that's just the fact that 2.4 is propagating a little bit further. So one of the things we recommend is tune down your 2.4 transmitter so that it covers roughly the same size cell as 5 gigahertz. So then your client device walks into that cell, sees the boundaries on both frequencies is the same and has equal chance of discovering both protocols or both channel bands. In the early days, just to get client devices connected, and again, because they could transmit further, they have higher SNRs to get higher data rates, devices tended to prefer the 2.4 gigahertz band, so clients naturally would move to 2.4. And in order to get around that, one of the earlier tricks was kind of what you described, was a psychological trick. You might name your 5 gigahertz SSID, NANOG fast, and your 2.4 just NANOG. If you could see NANOG fast, users think, hey, I want to be fast. I'll connect to the fast SSID. And you naturally move them through mind tricks onto the 5 gigahertz side. That works for a little bit for a while. Some challenges with that is if you start moving between access points and you don't have enough coverage overlap between your APs, you can hit a 5 gigahertz dead spot, and your device won't roam onto another access point with a different SSID seamlessly. So now you're constantly manually flipping between SSIDs. Then band steering came along, so a lot of enterprise-grade vendors introduced band steering, and basically the concept is in here. When access points try to discover the Wi-Fi network, they send out probe requests on the 2.4 and the 5 gigahertz side. The access point hears those probe requests come on 2.4. It comes from the same MAC address, so the AP knows it's the same client. And it says, hey, you can talk on both bands. I want you to be on the 5 gigahertz. I'm going to ignore probe responses on the 2.4. Hopefully, clients, when they hear the probe response, come back on the 5 gigahertz, they'll connect, and then it naturally moves clients on the 5 gigahertz side. Some clients were stubborn. So no matter how many times you told them, hey, connect on 5, they're like, no, 2.4 is where I want to be. You talk to 4, they'll connect there. So it can be a problem. So you can tune your band steering to try to compensate for that. But as technology evolved, the radio chipsets have got better. There's been more pervasive 5 gigahertz based designs. Now devices based on their algorithm are preferring to connect on 5 gigahertz. So in some rare situations, we're actually seeing problems turning on band steering. I mean, it depends on your environment and the types of devices connecting, but now clients will tend to prefer 5 gigahertz. But if we look at the iOS example that we talked about, devices are going to connect to the strongest signal. They might prefer 5 gigahertz, but if the 2.4 gigahertz signal is strong enough, that's where they'll end up. And they might not flip until you either kick them off the network by sending a deauth frame or providing them some better information about your network, what channels are available to them. But you need devices to support those protocols. So that's the 11K and the 11V protocol. A lot of enterprise APs will support those. Clients are just coming on board to support those protocols. But it's a very difficult problem to have, is to force users onto 5 gigahertz.
So not really is the answer. Okay.
Yeah. Yeah, so if you have influence on the client devices, either speak with your wallet and only buy client devices that support 5 gigahertz, or start phasing them out of your network. There's a gentleman yesterday who talked about making a drop-dead date for IPv4. If we can make this Friday a drop-dead for 11B, that would be fantastic. Sorry.
Hi, Carl Klatsky, Comcast. I got 2 questions if time permits.
Yeah.
First is, if you could just touch again on spatial streams. I didn't quite follow how those fit into the story.
Okay. So spatial streams, basically with multiple radio chains, it allows us to send additional information all at the same time across the same spectrum. So using the same frequency, we're sending independent streams of data, which basically it's like taking multiple paths and placing multiple sets of information on each of those paths all at the same time to get that client device. Is that?
Yep, that's good. And the second question was related to, you showed the heat maps and you're showing them a lot in 2D, XY coordinates. Is there any additional considerations or challenges you have to look at in heat maps when you bring in multiple floors, like here in a hotel or an apartment building?
Yeah, absolutely. Fundamentally, RF is a 3D phenomenon. The maps I showed you, that they were based on 2D. So Ekahau is capable of doing 3D modeling, but you should definitely look at that. So if you place an access point on the second floor here, when it shoots directly below, it's within that 10 or 15 feet. There's not a lot of loss through free space path loss. You might see maybe 10 dB loss through a thick concrete floor, but still you could, if an AP was directly above me in the ceiling here, I might hear it. High 60s, low 70s, fairly strong. So signals propagate well in three-dimensional space. So you should, whenever you're putting together designs, always think in 3 dimensions. One simple way to think about it is if we had multi-story building and we're deploying 4 access points on each floor, is offset them. So you might do like a plus on one floor and then put the next floor APs in the corners and just alternate that plan as you go up and down the buildings. But it depends on the layout of your building, but signals absolutely propagate between floors. Yeah, so some people use that in their design. Some people try to design that out of their other map. All right, I think that's it. And I believe it's lunchtime now, so thanks again for the session. And